Now, for the same mass moving in the same way as was the case here, we say that the angular acceleration at this instant is 4 radians per second squared. Okay, that's the rate of change of angular velocity. Units of angular velocity, radians per second, divided by units of time, seconds, radians per second squared. Okay, now I'm not quoting a formula here as much as saying that if we multiply a radian of angle by the 40 centimeter radius, we get centimeters of arc. So 4 radians times 40 centimeters per radian gives us 160 centimeters of arc, and that doesn't affect the second squared. So we can take our angular acceleration, multiply it by this radius to get our angular to get our acceleration, the actual acceleration in the direction of motion of this 100-gram mass. And from that we can easily get the force required to accelerate it. Force required to accelerate this at 160 centimeters per second squared. Well, force equals mass times acceleration. It's going to be 16,000 dynes, or 0.16 newtons. Okay, where's that force come from? Well, it might be something actually pushing on that mass, or something might be accelerating the beam, and the beam in turn accelerates the mass. So that 0.16 newtons could come from something external. It could come from the beam, which is being accelerated by something else. But in any case, it's going to take 0.16 newtons to accelerate that mass at this rate. Yeah, that's right. For a minute there I was a little worried about the significant figures. Okay, now in the next video we're going to move on and talk about torque and how that plays into this whole picture.